Yeah,
May I start?
Away.
Okay. Good morning, everyone. Welcome to Symposium for Quantum Undergraduate Inquiry and Discovery, better known as the S.Q.U.I.D conference. I hope this three-day event proves to be inspirational experience for all of us. Today, my friend Drew and I are happy to present this keynote speech. Please feel free to ask any question you may have in chat. Our team of organizers will be monitoring the Discord. So take the @Quantum Coalition role with any question related to the organization of the conference. My name is Melike Aydemir. I am one of the organizers of this year's S.Q.U.I.D as a second grade physics student and co-founder of Izmir Institute of Technology Physics Society.
Hi, everyone. I'm Drew, another organizer for S.Q.U.I.D this year. I study physics and mechanical engineering at the University of Maryland in College Park and serve as the events director for UMD's Undergraduate Quantum Association. Professor Andrew White is a professor of physics at the University of Queensland and the director of the Australian Research Council Centre for Engineered Quantum Systems, an Australia-wide 14-year-long research effort by 180 scientists to build quantum machines that harness the quantum world for practical applications. Professor White is a world leader in quantum technology, making contributions to fundamental advances such as quantum logic gates, simulation and emulation, quantum metrology, as well as other methodical advances in entanglement engineering, quantum tomography, and optical vortices. Professor White's research interests have spanned a myriad of diverse topics from shrimp eyes to nuclear physics and, of course, quantum computing. His current research focuses on engineering new technologies and scientific applications by exploiting the full range of quantum behaviors, especially entanglement.
We are grateful for the opportunity to hear Professor White. Will share some of his journey through quantum information science and his valuable research insights. Please welcome Professor White.
Thank you very much for that very generous introduction, and good evening and good morning to everybody joining us from Turkey and North America. I'm just going to share my screen. Here we go. And minimize, there we go. So I'm going to talk to you today about rise of the machines, making better photons by getting rid of experimentalists. This is work done at the University of Queensland. My website is quantum.prof. Our lab is quantum.technology, and we're part of the Centre for Engineered Quantum Systems, as you've already heard. All right, just to kick things off, I thought I'd show you all where I'm joining you from. This is the world map that we use in Australia. Brisbane is that red dot in the middle top of the screen there, and as you can see, it's kind of center of the world. It's equally far from everywhere. So I'm talking to you today in the US and Turkey, so it's a real pleasure to be talking to people from down under. You're getting to see me, but of course I get to work with a very talented team of students and postdocs. Seb, Fatima, Ming and Emerald are our current PhDs and honours students. Marcus and Marcelo are my two postdocs, and we've been collaborating with Aaron Tranter at the Australian National University, and we've currently got two of our PhDs have handed in and they're just waiting for their exams. Two more of our PhDs have just gone off to become postdocs at institutions around the world, and Aswa, I'm very proud to say, has become a lecturer at a university in Malaysia. Also, a bunch of our postdocs have just recently left us to go off to jobs in academia and industry, and I'll say more about that a little bit later. So everyone highlighted in orange here is worked on the material I'll be showing you later in the talk. All right, I thought I'd start before I jumped into the technical end for just a little bit of background on technology revolutions. So, you know, if you look at the big technology revolutions over the last few hundred years, steam, electrical, digital revolutions, and they all had a discovery phase which involved elucidating the underlying science, you know, thermodynamics for the steam revolution, electromagnetism for the electrical, and semiconductors for the digital revolution. But they also then moved to a kind of engineering phase where the concepts and discoveries got engineered into kind of standard technologies. Now, interestingly, the period for each of those engineering phases for each revolution has been halving for each subsequent revolution. So you could argue the steam revolution took about 200 years. electrical about 100, the digital about 50. And the second quantum revolution that we're entering at the moment, it looks like it'll take about 25 years. So you guys are incredibly well placed to be movers and shakers in that revolution. Just to look at the engineering phase for steam, shown on left is an early steam engine from 1698 in England. Those two round things here are actually kind of buildings built to generate the heat and steam necessary to pump water up from a mine. Within about 100 years, that led to some of the first steam engines for moving things along. The 1802 one at top rolled along on the ground. The one at the bottom is a very interesting idea. The first steam engines weren't very powerful and they had problems going up hills. So people looked around and realized, well, look, horses walk up hills beautifully. So that 1813 engine was something called a steam horse, and it literally walked its way along a track. Now, it didn't become a standard technology. The standard technology is the kind of steam engines we're all used to from the movies or Harry Potter or what have you. This is one built just up the road from where I live here in Australia back in 1899. All right, so in terms of quantum systems, all of the digital technology are from what we call the first quantum revolution, and I'll talk more about that in a couple of slides. But if we have a look, say 40 years ago, this is the supercomputer I wanted when I was much younger, the Cray XMP. It took a room to house, it needed its own air conditioning plant and a staff of 2 to 3 people to run it. And the quantum systems in that, being the transistors and the diodes, were by modern standards large, rare, there wasn't many of these things around the world, and expensive. With 40 years of engineering, these systems are now small, ubiquitous, and cheap. And my example of that is, here's the iPhone 4 from 13 years ago. You can buy one on eBay for between $20 and $30 US. And you should, because if you do and you pull one apart, what you find is not only is it mostly battery and screen, but there's a bunch of small control systems, which are fascinating, and sensors, of which more in a second, and a computer, which, by the way, is more powerful than that supercomputer from 40 years ago. And this is now a throwaway item. No one wants an iPhone 4 from 13 years ago. If you look at the sensors that are in there, there's electromagnetic sensors, RF antenna, GPS, magnetic field, capacitive touch, mechanical sensors, accelerometer, gyroscope, noise cancelling mic, and optical sensors for the cameras. If you take just one of these bits, and you can get friends who have an electron microscope. So for example, if you take the accelerometer and kind of carve off the top and look at the chip that's inside, and you keep zooming in, what you will find is highly detailed mechanical structures that have been built. So those veins shown at the bottom right on the slide with the 2 little red arrows, those 2 little red arrows are showing the kind of smallest regularly engineered feature in that, and that's about the thickness of a red blood cell. And humanity is now able to make these things at high volume, at low cost, such that after a decade we throw them away because we're now interested in other things. So if we continue along this path of technological change, then in about 20 years, which probably seems a long time to you right now, but when you get to my age, it doesn't seem that long, everything that fit into an iPhone 4 will fit inside a red blood cell. Now, for that to happen, we're going to have to make some more advances. We're going to have to figure out how to make biological and chemical sensors. We're going to have to figure out how to make power sources that are that small, perhaps power sources based on biology. But that's the kind of path we're on. So the first quantum revolution is all technology from the second half of last century that's electronic or photonic. So photocopiers for disseminating information, or solar cells for generating power, or lasers for everything from scanning groceries to eye surgery to cutting genes, through to satellites for long distance communication, and of course, mobile phones. All of the technologies in there are either electronics or photonics based upon the wave-particle duality. So it's just this one piece of quantum physics. So that is why we call it the first quantum revolution, because wave-particle duality is certainly a quantum phenomenon, But of course, there's more to quantum than that. Now, interestingly enough, nearly all of those technologies in the last 10, 15 years have hit a performance wall. Perhaps the most obvious one is processor speed. So here is a top-of-the-line MacBook Pro from 2006, and it had a 2 gigahertz processor from Intel. 10 years later, it had a 2.5 gigahertz processor from Intel. Now, if you're my age, that's actually kind of peculiar because when I was a much younger person, processor speed doubled every 18 months. That was Moore's law. And had that kept up, you can see that stopped sometime in the mid-noughties. But had that kept up, then it would have been a 203 gigahertz processor by 2016. And this year, it would be a 2 terahertz processor. The thing would literally be glowing with light. One of my favorite examples of a wall in performance is in magnetic resonance imaging. So in 1996, the kind of strongest magnetic field that people could regularly make for doing imaging on humans was about a 1.5 Tesla magnetic field. And this is an image of a human brain taken with that. After 10 years work, people doubled that up to 3 Tesla. And now the white arrow is showing a little feature in the brain, which is bad news for the person who has it, in that that feature shouldn't be there. But really good news for the person who had it, because once they discovered that feature with the MRI, they were able to treat it with positron emission tomography, PET, and the person lived. So that's 3 Tesla after about 10 years. Another 10 years of work got that up to about 7 Tesla in 2016. And I don't know if you can see it on your screens, but that last image is considerably sharper than the ones all preceding it. But that's pretty much the limit. We can make stronger magnetic fields, and we do for imaging things like materials, but it's no good for humans or any biological system because it starts hyperpolarizing the water in the animal or the human or the plant that you're imaging, and it starts appearing as speckle, which reduces the signal to noise. So after 20 years work, we've reached a limit to signal to noise. And also, if you're a physicist, 20 years of work to only increase the signal to noise by a factor of 10 is kind of terrible. Surely we can do better than that. So it doesn't matter what field you look in, whether it's solar cell efficiency, clocks and timing, battery efficiency, sensing, they all started hitting performance limits or noise floors or speed limits in the last 10 to 15 years. And in many of these fields, these went by the name of quantum limit, quantum noise limit, shot noise limit. And what it turns out is they're not really a limit. They're due to the fact that we're only using wave-particle duality. So the second quantum revolution is where we say, look, instead of engineering just wave-particle duality, we now use all of the features of quantum mechanics and engineer it into our technologies moving forwards. So the first of those is superposition. I'm sure you've all come across this in undergraduate already. The idea that classically something can be here or there, but quantum mechanically, it can be here plus there, or here minus there, or here plus I times there. It doesn't really matter. The second one is entanglement. And entanglement, of course, there's really no easy description of it, because if there was, we'd be used to it and it wouldn't be surprising. But it's correlations between quantum subsystems or separate quantum systems that defy a common sense explanation. If you had entangled cards, you could always win at a casino, but they'd probably nail your hands to the table. So I always think of it as entanglement is nature cheating at the very fundamental level, and we'd like to learn to cheat as well. And finally, of course, there's quantum measurement. In classical systems, the act of observing the system doesn't change it. Looking at an apple doesn't change its color or change it into an orange. But in quantum systems, of course, the act of observing system very significantly can change the system. So these three things we will engineer into the application areas that people have now identified as benefiting from the second quantum revolution. The first of these is sensing and imaging. So the image shown at top left is a nanodiamond hovering in a laser beam focus. That's work being done by colleagues of mine at Macquarie University in Australia. And the image at right is MRI of a biological sample done in their lab, where they injected nanodiamonds to get better MRI. So now you can get far better resolution than you can with normal MRI. You can even see inside cells. Before anyone worries about this particular biological sandwich, it's a slice of cucumber, and they were able to eat it on their sandwich afterwards because diamonds are biocompatible. The second area that's been identified as benefiting from quantum technologies is quantum simulation, simulating hard problems in biology, chemistry, or physics that we currently can't do with all the computational power that we have. So shown at left is caffeine, which is my favorite legal molecule. It's about 30 atoms, and you can model a full quantum mechanical model of caffeine on your laptop. But what you can't do is cholesterol, and it's only 100 and something atoms. And you certainly can't do something with thousands of atoms, not with every computer in the world, because it turns out if you're trying to model atoms accurately, every time you add an atom to the molecule, you double the computational time. So that kind of exponential blowout means it's a problem for classical computers, but for quantum simulation, that's a way forward. And that brings us more generally to quantum computation, of which I'm sure we've all heard. There are numerous problems identified as benefiting from quantum computation. If you go to something called the quantum algorithm zoo, there's at least 40 different algorithms there, but there's just 2 or 3 that people think will be very significant moving forward. We don't really know what the killer app is yet for quantum computation. I certainly have an opinion, and we can talk about it in Q&A if people are interested. Metrology, the science of measurement, timing for precision navigation and timing definitely gets better with quantum technology, and that's already starting to roll out into the field. For example, how do you navigate in a GPS-denied environment? It might be denied because of building structures. You're not able to see the satellites. It might be denied because someone's playing Pokemon Go and they're doing a jamming thing so they can move around. All of this has happened. Secure communication, everything from verifying a link is secure using quantum phenomena through to multi-party voting protocols, which are not possible classically, are possible with quantum communication. And then finally, and not least of all for this audience or for me, the discovery of new physics. So shown on the left of that last image is the distribution of dark matter in the local group, and people are now looking for that using various quantum technologies. And on the right is an image of gravity waves emanating out from some astrophysical event. And LIGO in the last few years has been using squeezing to vastly enhance its search volume, reducing its sensitivity under what had been the quantum noise floor. So that is very definitely the first use of quantum technology to engender new science. Before I go on, are there any questions or thoughts or comments people have on that stuff? I'm happy to look at them in the chat or take them over audio if people want. Otherwise, we can leave them to the end. All right, nothing going. I'll keep going.
Maybe we can wait it then.
Okay, fair enough. International context, just how is the world reacting to quantum technology and the challenges and the potential? So this is a slide presented at a European Union meeting earlier this year, showing some of the investments last year, as of last year, in North America, in Europe, and in Asia. And there's many more investments than shown in this slide, but it'll give you the kind of sense of it worldwide. Depending on what country you're in, your country may already have a national or, in the case of Europe, European-wide quantum strategy, and many more are coming. So do have a look at those if you get the chance. And I guess the other thing to say is with this amount of investment globally, if you're a graduate in quantum technologies at the moment, the number I saw most recently is for every person we have graduating, there are 6 jobs that they can go to. So there are many more people looking for graduates in quantum technology at the moment than there are graduates. So this is a great time to be in the field as well. All right. So let's talk to you about rise of the machines, making better photons by getting rid of experimentalists. So one of the things my lab deals with is quantum photonics. That's where we're encoding the information in photons for various tasks. There's 4 things you need to do to make quantum photonics work. Firstly, you need a source of true single photons. The second thing is you need to be able to have them interact with each other through linear, low-loss reconfigurable networks. The third thing, ideally, is you'd love to be able to turn on nonlinearities in those networks. So a single photon could, for example, change the phase of a single other photon. And then fourthly, you need to be able to detect those photons with fast, efficient, quiet, broadband, number resolving detectors. Now, there are globally research programs in all of these areas and great progress. So today, I'm not going to talk about the nonlinear networks or detectors, although there's brilliant stuff I could talk about there. We're just going to look at improving the photons in the linear networks using machine learning. Okay, so I'm going to, in the next 30 minutes or so, briefly look at making better photons, gathering more photons into fibers, routing them more efficiently to where you need them to go, and keeping more of them in photonic integrated circuits, all using machine learning. Now, what's machine learning? The definition I like is it's just any process that attempts to distill some known algorithm for solving a particular problem using a computer. It comes in three flavors, really. There's supervised, where you kind of look over the machine as it's learning and guide its learning. There's unsupervised, and that one's fascinating. That's where the machine will find structures that you yourself had missed. And then there's reinforcement learning, which is kind of you keep giving it treats as it heads off in the right direction. We use all three in various ways in our lab, and I'm going to talk through that now. This slide was adapted from Aaron Tranter at ANU. So making better photons, this was work done by Ji-hun during his PhD. Ji-hun joined us from South Korea. What's the ideal single photon source? So if you write it down, it's this equation. But really what it is, it's something that has a definite polarization, a definite spatial frequency and spatial distribution, a definite angular frequency and spatial profile as shown, and a definite number of photons. And ideally for a single photon source, you want that number to be 1, shown there in red, and only 1 photon. And you don't want there to be any vacuum. So if there's a pulse, you want every pulse that turns up to have 1 photon, and you don't want any to go missing. And you don't want it to be mixed with anything else, including higher order terms. So if I'm going to sell you a single photon source, how do you know that I'm selling you something that is giving you single photons? Well, the very first measurement you do is you send your stream of single photons towards a photon detector. And you look at what is the probability in a given time window of getting a click that says there was 1 photon. And you can use detectors that will tell you if there's 2 or more photons, but you want to know how often is there 1 and only 1 photon. The next thing is you put a beam splitter in front of that detector, a 50-50 beam splitter, and a second detector, and you ask, how often does a photon arrive at both detectors? Now that number ideally should be 0. That should never occur. So in the lab, we take the ratio of those 2 probabilities and we calculate something called the G2. 1 minus the G2, so ideally G2 is equal to 0, and 1 minus G2, which is the multi-photon suppression, is equal to 1, or 100% suppression of 2 or more photons. And this generalizes as well if you're trying to make a 2-photon source or a 3-photon source. You can measure this quantity. The other characteristic you really care about in photons is something called the indistinguishability. Photons can be ideally completely indistinguishable from one another. And if that happens, if I take 2 streams of indistinguishable photons and mix them on a 50-50 beam splitter, a very strange thing happens. I get basically Bose-Einstein condensation. The 2 photons clump together and both of them either go to one detector or both of them go to the other detector, but they no longer separately go to the detectors. This was first, so you measure that by measuring first the coincidence when the photons are as indistinguishable as you can make them. And then you might change the color of one of the photons, the polarization of the one photons, or the time that they arrive. You make them distinguishable in some way, and then you measure that coincidence rate. And the ratio of those 2 coincidences was first proposed, this interference technique was first proposed by Hong, Oh, and Mandel in 1986. So it's called the Hom visibility. And ideally, that would be 100%. Now, in the lab, we never get to 100%, but we can get quite close, as we'll see. Skip on. So in our lab, we have a number of ways of making quantum dot sources, but the ones that we're improving with machine learning at the moment is quantum dots in micropillar cavities. So a quantum dot is an artificial atom made out of a mix of indium, gallium, and arsenide. And then we embed it between mirrors. These are these stripy structures either side of the red dots in the middle that are made of alternating layers of gallium and arsenide. And then the whole system has an electrical tuning to drive the electric field of the artificial atom to be resonant with the cavity. And we pump it with an external laser, and it emits single photons. It has very high multiphoton suppression. In the lab, we regularly get to 99% and above multiphoton suppression. The sources, this is an image of one of the sources, are very bright. You get 100 times more photons out of this than any other solid state source, because the cavity enhances the probability of that artificial atom emitting in the direction shown by the red spike. There's an 80% probability that the atom will emit in that direction, and only a 20% probability that it'll go anywhere else in the 4 pi steradian of angle there it would normally emit into. And the photons we make with this way are highly indistinguishable. Again, they're around 99%. So what are we doing with machine learning? Well, there's 2 ways typically that you can pump one of these quantum dots. You can come in with, say, a very energetic laser, shown here in blue, and excite the ground state of the quantum dot to well above the excited state, as shown here. And then you let the excited state relax in energy by various solid state processes till it gets to this dotted line in the bottom of the excited band there. And then it drops down, emitting 1 and only 1 photons. Now, the advantage of this method is it's very easy to pull the pump light away from the photons that come out because they're different colors, so we can use color filters to do that. The disadvantage is because that process of the excited electron kind of rattling around and coming down is different shot to shot and dot to dot, the photons that come out are quite distinguishable because different things has happened to the electron that produces the photon. So a better way to do it is you resonantly excite the dot. So you provide it with just enough energy it needs from the pump laser so that it produces 1 photon in a given time interval. The problem with that, now that's great. It avoids dephasing this electron rattling around. So the photons coming out are highly distinguishable. But the problem is now to get rid of the pump laser light, the photons all come out in various polarizations. The pump light was at only 1 polarization. So you cross-polarize to avoid getting that, but that means you lose half your photons. So there are other ways as well, but this is to start. So what we normally do is the issue that we're dealing with is the wavelength of the pump laser light doesn't match the cavity wavelength. So the part of the pump laser that overlaps with that red cavity shown in the middle gets absorbed, and that's great. And that the blue stuff on the wings scatters off, which you would think is not a problem. But because we're measuring single photons, the detectors are incredibly sensitive to scattered light, and it shows up as multiphoton noise. And multiphoton noise, as you increase the amount of multiphoton noise, so remember G2 should be 0, it's shown here on the x-axis. And as it goes from no multiphoton noise to more multiphoton noise, the Hongo-Mandel, shown on the y-axis, which should be unity or 1, drops down in direct proportion. So you want to kill that off. So how do we reduce it? One way is you could turn down the pump laser, but then you don't have optimal power for producing the single photons. So that's not really an option that you want to do. A second way that most people in the field did until recently is they just filtered off the excess light. But the problem with that is these filters are very lossy and they eat the photons that you're trying to make. So that's no good as well. So what we explored doing is retuning the pump laser with a computer programmable filter. And what that looked like is shown at bottom right. This is something called a 4F spectral filter. Shown at bottom right is an input pulse. It comes into a grating. All the colors in that pulse get spread out to different spatial modes. We then go through a mask, which is a computer programmable hologram where we can affect both the amplitude and the phase of those components. And then those components are recombined by a second grating and sent off to the quantum dot. This is great because in the real world, every quantum dot that you use is different. And they have a different, hard to find optimum set of operating conditions. So if we can computerize it, that will take much less time for me or the student in the lab, and we can just press a red button on the computer and have it go. Here's the quantum photonic chip that was made by colleagues of ours, and zooming in those little cylinders with crosses, that's our quantum dot light sources, and zooming in further, the actual semiconductor quantum dot is that little red dot in the middle. The photonic cavity that we're aiming the laser at is only about 3 microns wide, shown at the top. How did we do it? We picked some random pattern for the spatial light modulator, that mask that we're using. We sent it to the quantum dot. Typically, it was just terrible. We measured, say, the Hongo-Mandel visibility or the G2 value. And then we asked, was it better than the goal we set ourselves? And if the answer was no, well, then we go back through a control loop and randomly change things step after step after step until the answer is yes. Yay, and then we've successfully done things. So how many steps do you need? Well, it turns out we started with, this is a very typical day. Student walks into the lab, they adjust things by hand, and they get a 92% Hongo-Mandel visibility. And that's pretty good. Typically getting it up beyond there, though, can take anywhere from hours to days to weeks. So in this case, however, we turned on the machine learning, and within 8 steps, it hit our predefined limit where we said we'd be thrilled if it got to 96%, because previously we'd got up to 96% by hand, and it got there in 8 steps, taking about 10,000 seconds. That's when we were training the algorithm up. We achieved 96% photon indistinguishability and 98% multiphoton suppression, and we weren't even trying to increase that. That's just a consequence of us getting things right. No filtering. We recorded the parameters of that grating at each step, so we could recreate things a week later. So we can come back a week later, and in a much quicker time run, again in 8 steps, see a similar improvement. So machine learning gives you better indistinguishability, which is closer to single photons, suppresses multiphotons, so again, closer to single photons. It also made the source 3 times brighter, and we used 2 times less pump power, so it was 6 times more efficient, and again in about 8 steps. So this was great. Right, moving on to gathering more photons. This is work by Seb. He joined us from University of Wisconsin after his undergraduate and did a master's and is now doing a PhD with us. There he is cuddling a kangaroo, because apparently you've got to do that. So we had now got rid of the frequency filter shown here as lightened. Now we want to get more of the light into a fiber. The way you do that is here's a light source. You send it through a telescope onto a deformable mirror that changes the wavefront of the light. So when you send it through a second telescope, you get more of that light into a single mode optical fiber. The deformable mirror is a fascinating device. It's a silvered surface made by a company in France called Alpao, which has 69 micro actuators behind it, each of which can be controlled individually. So you can deform that surface in all kinds of ways. The machine learning algorithm here, again, start with random values applied to the mirror, shown here in this little animation. Take some counts from that on what you're getting, use that to do then a genetic algorithm where, again, you go back through asking, did the count rates improve significantly? And you need to define ahead of time what you're going to count as significant. But if the answer is yes, you say, great. You then use that to generate the next random set of patterns that you're going to feed to your mirror. And you keep going through that loop until the answer is no, there hasn't been a significant improvement. And then you say, look, I'm done. So again, how many steps do you think that would take? Well, we shown here, we were testing the system just with a laser beam out of a fiber, trying to get it into another fiber after it had been through some optics. This is the initialization step. And then after 6 generations of the algorithm running, we had a 35% improvement on the amount of light coupled. And again, very quick. We put a pinhole in the way to make a pattern on the light, so it was terrible and much less likely to go into the fiber. Again, 6 steps later, 45% improvement of the light going into the fiber. We shone the laser light that we used to pump our quantum dots onto the top of the cavity, the little quantum dot cavity. And again, 6 steps, 31% improvement. And now shown and bottom left, those scatter of pink dots now are the single photons coming in. And you'll notice it's very noisy. Before it was quite a straight line. I'll come back to that in a second. 6 steps later, there's a 66% improvement. Now that's much bigger than we were expecting. We thought it'd be around 30%. And we're not entirely sure we believe it because this is much noisier data than everything else, because it turned out our laser, which is water cooled internally, developed a leak, and it had turned into a small swimming pool which filled up with about a centimeter, well, an inch for the Americans, 1.5 centimeters for everybody else, of water, which was just short of the 10,000 volt element, which would have totally killed the laser. We found it in time. We've rebuilt the laser and we got the photon source working again yesterday. So we are hoping to take more measurements on this shortly. All right, routing more photons. This was work done by Fatima. She was one of our undergraduate students and she's now doing a PhD with us, I'm very pleased to say. So what comes out of these single photon sources is a whole bunch of different photons at different times, but in the one spatial mode. And that's great for circuits. You can build a quantum photonic computer this way using something called time bit encoding. And in fact, there was a paper out of Philip Volter's lab at the University of Vienna in Nature Photonics, I think 2 weeks ago, showing exactly this. But often you might want to demultiplex that so that you get n1 photons at the same time, but in n different spatial modes that you can send off to n different fibers, for example. And that's very useful for all kinds of circuits, particularly quantum photonic computing is more often done that way. I'm going to skip this slide and just say, look, one way to do that in the lab is you could come along with a photon that's, say, vertically polarized. You send it through a Pockels cell, which is something that changes the polarization of the photon with voltage. So you're going to turn that off for the moment, have it reflect off of a polarizing beam splitter so that it is now next to a second photon that comes in. Then you have both of those reflect, so they're next to a third photon. Then you have all 3 of those reflect, so it's next to a 4th photon. They're all now in the same time in different modes. You turn the Pockels cell on, so it changes vertical to horizontal, and that gets transmitted through the polarizing beam splitter, and you've done the job. We did that at first. It worked well. The Pockels cell we had was relatively slow. It only worked at 80 kilohertz. And there were other disadvantages. So what we really wanted to do was see, could we do it at 500 gigahertz, for example? So we worked with a group across the river in Brisbane at Griffith University, Mirko Labino and his team, who make waveguides in lithium niobate. So lithium niobate is a nonlinear crystal, but they indiffuse titanium oxide to the top, and that makes a place where the light is guided like it's an optical fiber. That's these colorful spots here is the intensity of the light, showing where it's localized to. And then the red boxes on top are metal that we deposit on top as electrodes. And then by putting voltage across those electrodes, you can change the refractive index. So you can make the light in one of these regions couple from one of these waveguides to another. So it becomes a voltage controlled switch. This system is very attractive in paper. It's low loss, 0.1 dB per centimeter. You get high coupling to single mode fiber, and you can drive it at 0.5 gigahertz. Shown on right is the theory of what we should have produced at top, and at bottom the experiment. It worked. Shown at left is the system in the lab. What you can't see is the crystal in the middle because it's transparent and it just sitting on top of the metal. It just looks like a piece of metal here in the middle. Here's the data when we first turned it on. So here we're trying to switch light from channel 1 to channel 2, and most of it goes there, but some goes into channels 3 and 4. Here we're trying to switch it into 3, some go into 2 and 4. We're trying to switch it into 4. Some go into 2 and 3. So it's okay. It's not wonderful. What you'd really like to do is squash those peaks away entirely. So we asked ourselves, can we do that with machine learning? We started doing it. The chip cracked. We repolished it, started doing it again. And the second time, the chip died entirely. So we had to move the experiment to a new chip from our colleagues, where now it's a binomial tree structure. This was optimized for light at telecom wavelengths at 1550 nanometers. So there's one electrical contact, which we call switch 1, that sends you into the top half or bottom half of the chip. Then a second contact that does the same thing again, a third contact and the fourth contact. So now there's only 4 electrical elements to tune, as opposed to a quadratic number growing. And this is a 1 to 16 switch. So ideally, for example, if I was sending light to only channel 1, 100% of the light would go up there and no light would go into the other 15 channels. The pulses we'd put on, well, what are the variables? You can change the pulse height, the voltage, the pulse width, the time. You could change the shape, but I'm going to come back to that in a minute. And so you can make out a matrix of increasing pulse height, increasing pulse width, and then you can, for every channel and every metal switch, do an error surface by hand. And this is what a student at Griffith University did. So here you can see the pulse heights varying from 0 to 20 volts, the pulse widths varying from less than 100 to 500 nanoseconds. And you take out a surface like this. And the color coding on this surface is red is good. You're getting a lot of switching. Blue is bad. So you can see in this case, it's mostly bad. And you can do that for channel 2, just looking at the voltages on switch 4, and channel 3, just on switch 4, and channel 4, just on switch 4. And each of these surfaces takes about 30 minutes, and to characterize the entire chip takes about 5 hours. So that's terrible. So we wondered, look, could you do better with machine learning? I'm going to skip through the details, but we basically used a simulated annealing algorithm. It's very quick, few lines of Python. And to cut long story to the short, we gave it the starting pulse width and pulse height, randomly picked. In this case, it was here in one of the blue regions. Within 5 steps, it had found the optimum. So it wasn't mapping out this surface. This is the surface we'd taken earlier. This is the machine learning finding the optimal point on that surface in 5 steps. So that's fantastic. It found, in each case, it found the optimal point on the surface, and it did it in 2 to 3 minutes. So an order of magnitude faster. So yay, celebrations. But the next steps to think about is, how can we improve things so that we do better than the surfaces we had. So we want machine learning to do better. So you can optimize the voltages for more than one switch at a time. So instead of just doing switch 4, you do 4, 3, 4, 3, 2, 4, 3, 2, 1. So you need to have a machine learning model with extra dimensions. We're working on that now. And also you vary the pulse shape. You turn things on smoothly on and off. Looking at the time, this is work done by Ming and his photons and integrated circuits. This is a really famous experiment from Zhenwei Pan's group in China. It was done during the pandemic in 2020. It was a boson sampling experiment involving, I believe, 50 photons. Every one of those pieces of optics there was aligned by hand by PhD students who were actually in the lab literally for 3 months continuously, because if they'd gone home, they weren't allowed back to the lab. So their boss, Chow Young Liu, was bringing in fresh clothes and food and leaving it outside the lab. They showered in the lab, slept in the lab, and worked in the lab for 3 months. And that's wonderful. It's literally a hero experiment, but it's not the way forward for a whole industry. So what we're moving towards is programmable photonic integrated circuits. These are made using silica on silicon, or vice versa. The earliest one in 2015 was a 6x6 circuit. The biggest one that's been shown that's not commercial to date is a 26x26 unitary. The problem with these things is they're incredibly lossy at the moment. So just going along those integrated circuits, you lose nearly 50% of your light. You also lose, going into the circuit and off of the circuit, 50% of your light. So the total loss is about 84% of your light. Also, it uses thermal phase shifters to do the tuning, and that's kind of slow. So what we want is new materials that are low loss, new designs for the components on the circuits, and we want fast switching. There's various components you can put onto these circuits. They fall into three categories. Passive control components, things like waveguide crossings, coupling light on and off the component with gratings or directional couplers. And then active components to do the phase shifting. And they fall into three categories. Thermal, which works at kilohertz, mechanical, microelectrical mechanical systems, which are terrific fun to make. They work at megahertz, or electro-optic or electrorestrictive that work at gigahertz. In our lab, we've been playing with lithium niobate, which is low loss and electro-optically active. Silicon nitride is our workhorse material. It's low loss, not electro-optically active, so you can't use it for switching, but it's really good for testing circuits initially. And silicon carbide is the new wonder material coming onto the market, and we've just started making circuits with this. When you're trying to make these circuits, what you used to do in the old days was design, say you wanted a coupler, two waveguides close to one another, so the light tunneled from one waveguide to the next. Well, that needs a certain length of interaction and a certain distance between them. So you might make 200 of them of a chip, 100 where you're varying the length and 20 where you're varying the width. And you then have 200 combinations. You build them all, you then test them all, and you find 5 of them that work. So the yield on these things is really low. That's conventional design. But the last few years has seen the introduction of something called inverse design, which is incredibly high yield. It works first time, and it works in a way that no one understands because it's machine learning. So I'm going to show you a famous example of that. This is from Jelena Vukovic's group in Stanford University. What they gave the machine as a task to solve was, I have a waveguide coming in with 2 colors of light, say red and blue, and I want the red to go into one output and the blue to go into another. And I want you to design a circuit to do that. Here's what the fields will look like in the circuit. So that's what the machine learning is working on. And shown at bottom right is the structure that the machine said to make, showing the predicted performance for the blue light going to the top and the red light going to the bottom. Now, if you look at that, there is not an optics engineer alive, an optical physicist, a quantum physicist. No one would have predicted that structure ahead of time. They built, that's the prediction on how well it will work. Basically, the red curve should be higher in the right half, and the black curve should be higher in the left half, and the other curve should be correspondingly low. They built it. That's the first one they built, and it worked first time. And that was nearly unprecedented in this field. So that's changed everything. The way we fabricate these in the lab is you have, say, a thin layer of silicon nitride and silicon oxide. You put some resist down. You etch away the excess silicon nitride. You take the resist off the top, and then you overcoat with silicon oxide, and you've now made your integrated circuit. We've been making grating couplers, waveguide crossings, directional couplers. I'm not going to take you through all the details now because I'm aware I'm out of time, but basically the systems we're building has been improving things from the best people had done previously with 78% for getting light. So I have one waveguide, it crosses another one. Normally it loses light into that second waveguide because it's a slit. The process says, no, make a crazy looking thing. And then when we do, we get a big improvement in performance. Similar for grating couplers. This is where you have light coming in at nearly right angles to the surface of the chip, and then it basically acts as a little micro antenna, except working at the visible wavelength that then takes the light and sends it sideways. So it takes it nearly through a right angle in space. The efficiency, typically, the best people were doing was about 11%. Our new designs are either 68%, or if we put a metal behind them, 83%. So an improvement of 6 to 7 times. So look, what's the take home from all that? Machine learning in the lab at the moment is giving us more photons, better quality, more efficiency. It's giving us more photons into optical fiber. It's giving us optimal switching voltages 10 times faster. It's giving us better performance on these chips, and it all takes much less time. So using these modern tools in the lab lets us get to the physics we're wanting to do a lot quicker. So with that, I'm just going to finish on a note that any prediction I make about forward technology, I'll probably be right in the big picture, but probably wrong in the details. And my favorite example of that is this is a smartwatch, the Apple Watch, introduced in 2015. And you'll notice it's being interacted with a thumb and forefinger. That was first predicted in 1981 by Byte magazine. They had the idea of a computer on the wrist. They had the idea of the thumb and the forefinger doing the interaction. They just got the details laughably incorrect. And everything I've told you today might look like that 10, 15 years from now. So with that, thank you for your time. And if there's any questions, love to hear from you. I'd also put an ad up. We have PhDs available and master's scholarships available. 26,000 US, 540,000 Turkish lira, tax-free. Please apply. Thanks for your time.
Thanks for kind acceptance and your speech. Thanks a lot. Check question.
Yeah, so we're going to start taking questions now, both from the YouTube chat, if you're there, Zoom over here. So if anyone wants to ask a question, you can either raise your hand and unmute or just pop it in the chat. And then after that, I'll go to some of the questions we have on YouTube. Okay, while we wait for that, was there
I'm happy to ask a question if there's space. I don't want to crowd anybody out. But so could you you mentioned that you have opinions about the killer act of quantum computing. And
I do.
Yeah, and I kind of wanted to ask about that, and also sort of about this analogy you made to the development of classical, technologies such as like the steam engine. Do you think that maybe, so the first part of this question is, what is your opinion about the killer act of quantum computing? And is it possible that the way that we're thinking about quantum computers today is sort of equivalent to the steam horse?
Yeah.
And are there other places where you think that this technology could go?
Yeah, I'm really glad you asked that, because that's why I've got the steam horse slide there. It was not at all obvious to people at the time what the optimal solution would be. Okay, so look, I think the first exciting applications of quantum computing will be solving problems in science. Battery chemistry for an automotive manufacturer, better understanding about maybe people like to say the Haber process in chemistry, although that's quite a tough problem. But, that kind of thing, materials problems, chemistry problems that we know are hard. But I think long-term, the real killer app for quantum computing is something called blind quantum computing. So this breaks Google's business model, but it supports Apple's. So at the moment, if I am sending a query from my computer to the cloud, it might be a photo manipulation, it might be a search query, it might be an email. That information needs to be known by the cloud. It knows the calculation that it does, and it sends it back to me. So there's no privacy. However, there's a thing called blind quantum computing where I can send a quantum state to a remote server, a remote quantum computer. It does a calculation. It does not know the quantum state. It does not know the calculation that it's doing. And it sends me the answer back and does not know the answer. And I have full privacy the entire time through that process. And that's classically impossible. It's been talked about in classical computing, and they've shown that it takes basically an infinite amount of energy to do. That's where the exponential blow up is. And quantum computing can do that. So once quantum computers get big enough, I think that's going to be a very compelling use case for a bunch of things.
Wow, that's fantastic. And is that something that I guess I've heard proposals for blind computing with like measurement-based quantum computing, or leveraging like channel state duality?
Okay, so blind quantum computing itself is kind of platform agnostic, whether you're doing, measurement based or not. It does, so some of the early work that was done on it, there was an early experiment, again, out of Vienna, I think Philip Volter's group, and there was early work by Anne Broadbent colleagues in Canada on it as well. So yeah, we shall see. And look, I could be wrong. I think the people who have made the first transistors in the 50s, no one guessed that the use case of that 60, 70 years later would be people capturing virtual critters at the bus stop while listening to music, right? So, who knows?
Yeah. So a question we had from the chat was relating to your discussion on waveguide chips, and they were asking about how you would prevent third order nonlinearities and how you deal with single modes both in the second and third orders. Okay, so one of the ways that we can avoid third order nonlinearities is the amount of light in there is incredibly low. It's only ever single photons in there. So we're not ever in the regime where you need to worry about higher order nonlinearities. Having said that, I would actually love higher order nonlinearities in the cases where I would like a nonlinear interaction between single photons. So there have been people looking at the fact that when you do have these nano photonics, you've got very high field concentrations. And if you do it in a material like lithium niobate, you can, for example, the Chi-2 nonlinearity there is enough that you might start getting phase shifts between photons and in that regime. If you tune that away down to the zero of the sync-squared function, where normally the Chi-2 turns off, there, however, you get an effective Chi-3 nonlinearity, which is what you want for phase shifts, but it's at basically just pi times weaker than the Chi-2 nonlinearity. So the people are playing with these systems. And frankly, we would love to have some nonlinear processes, but we're so weak that we don't worry about the normal parasitic processes at all. Yeah.
Another question from chat.
Please.
What type of ML algorithm was used in making better photons?
Right. So that one was, just go back. That was just a really simple feedback loop, where I believe that one was a genetic algorithm, I think. So nothing very sophisticated. We weren't doing anything, particularly random. But I'll be honest, I can't remember right now. It's about 1:30 in the morning here, and I'm blanking a little bit mentally. But if the person writes to me, I can look it up and write back to them with the detail exactly. So I don't tell you the wrong thing.
Sounds good. Yeah.
Thanks.
Just checking the chat for questions.
No worries.
I think we'll take one more question since it's just about 11:30.
So I have a question. How do you see the photonic quantum computing among all the other techniques like superconducting?
I was wondering if I get this question. Yeah. So let me, it's a really good question. And let me say, up until the last couple of years, I've been very skeptical about the claims all the companies in the field were making, because early on, the claims were very ambitious without any track record of actually seeing progress. But in the last few years, in the superconducting space, for example, from IBM and from Google, we've seen, results, steps along the way, and they've got a clear roadmap. And from the photonic end, S.Q.U.I.D, who are based in Silicon Valley, have recently come out of stealth, showing some incredibly sophisticated engineering. And so we can only talk about what they've just recently announced. So IBM have come out and said 10 years from now, in 2033, they would like to have 100,000 physical qubits. And they've released, I think it was in a video last week, a kind of sketch of the architecture they see to get there. So Quantum have said 5 years from now, in 2028, they aim to have 1 million physical qubits, which will give you about 4,000 logical qubits. And 1 million is roughly the magic number, because if you've got 1 million physical qubits with the kind of normal overhead that you have with error correction, that gets you a few thousand logical qubits. And at a few thousand, there are problems that have become very interesting now, either scientifically or commercially or both. So if you're asking me, who will win? I really don't know, but I'm a gambling person. So I'd put $1,000 down that S.Q.U.I.D will have built on the order of 1 million physical qubits by 2028. If I'm allowed to spend your money, I'll bet $1,000 by 2027. But my money, I'm going to go 2028. Now, that doesn't mean that means they've won. That just means they're the first person to get to that number. There are a bunch of issues that are going to come out in the engineering these systems, and I don't think we yet know. We don't know yet which one is the steam horse and which one is the steam engine. But it's a fun time to try and find out. I do think to get to 1 million of anything, you really do need proper engineering, the kind of thing we do in our lab. That lovely photo from, let's see if I can go to it. That lovely photo from Zhenwei Pan's lab in China. This is not going to suffice, right? That was 50. 1 million would kill people. So one of the advantages S.Q.U.I.D has, I think, over many of their other competitors, is they're using tier 1 fabrication facilities that regularly churn out millions of devices that are identical. So we're going to need to develop approaches like that. But what's really exciting from a physics point of view is once we've got machines like that, there's some really great physics we can start doing with them as well. So I frankly can't wait to get my hands on one.
Thank you for your answer.
Thank you for the question.
Yeah. Thank you so much, Professor White. This has been an incredibly engaging and amazing time listening to you speak. And for everyone tuning in, this wraps up the keynote portion of the event. Let's give Professor White a huge thank you for staying up so late to be here and to join us for this amazing conference. So thank you so much.
Look, thank you very much for the kind words. Apologies if I was a bit sleepy. It is late here. And the very best of luck with the rest of the conference. I would stay tuned in, but I'm killing for a sleep now.
Get some rest.